Hi, I'm Rich with insideHPC. We're here at the Allinea booth at SC12 in Salt Lake City. I'm here with Mark O'Connor. He's the architect of a new thing from Allinea called MAP. Mark, what is MAP and what does it do?
Allinea MAP is a different kind of profiler. So we've had a lot of these classic trace-based tools that are great for the experts, tools like Tau or Vampire or Scholastica. We work with those guys, we've got a huge respect for them. And their tools are great for really drilling down into fine detail. But for the classic scientist, as a scientist, I don't care about the tool itself. I want to get my science done.
Right.
I may not be an MPI expert. So we looked at this situation and we thought, what can we as a commercial company do to help out here and to contribute to the community in a way that open source or academic projects might not have the resources or the manpower to do?
Okay, well, can we take a look? How's it work?
Yeah, how's it work? We try to make it as simple as possible. So everything that's special about MAP is the things we've taken away, if you like. So we've taken away the need to instrument your code. You don't need to compile with any special options. You can just run MAP on your program just as it is. So we've got a demo program here. You just run it as you would with MPI run. And just like DDT would, MAP can submit this to your queue on the cluster and do everything overnight for you. That's all fine. We're just going to hit run here. So off we go. It's built on the same architecture as DDT, which means MAP also scales to very high scale. It's not a problem for us.
So it's running some kind of analytics right now on the MPI, or what's it doing?
Yeah, so what's happening here, our demo program's running through, it's producing a whole bunch of data, and MAP on the cluster, or in this case the laptop, is monitoring that. It's doing sort of regular sampling through the job to keep an eye on what's going, and it's generating for us the big picture of what the program actually does while it runs. And it's doing all of this with very little overhead. We see typically 5% overhead on the program, even at very large scale, thousands and thousands of processes. All right, we don't need to wait around here, so let's have a look at the results.
Okay, so what are we seeing here?
Yeah, so after running MAP, this is what you see when you load a trace file. It was very important for us to get the source code up front and center, because as a scientist who's been trying to implement my model into Fortran 90 or C, then the source code is my only point of reference here. This is what makes sense to me and what I need to change to make the performance better. So we've got the source code here, and over to the left, we just annotate that with the performance information about each line of your code. Green here, green is always time spent computing. This is generally good. This is time spent on the floating point units and so on. Blue is time spent communicating or waiting in MPI. So as a rule of thumb, you want a lot of green and not very much blue, and then you're scaling well. So what we see here, you can see at the start, we're calling imbalance first. This is all across time here. So left is the start of the job, we do imbalance, and then we go down and we spend like 26% of the time in stride, and then the rest of the time in this very inefficient looking overlap function. And we can just zoom in. Let's have a look at this imbalance function in more detail. I'm just zooming in here with the mouse, and then the view redraws and shows everything in detail. Down here, the parallel stack view, if you've used something like gprof for profiling a single process, this is very familiar to you. It's showing the functions and how much time was spent in them. Again, we can just expand out. So this here is our imbalance routine and the actual source code. We see here a lot of compute time spent on this square root, and all of the rest of the time spent in this all reduce. And you can see here kind of lots of little iterations going through the code, kind of this repeating pattern. Let's just zoom in on a couple of those and see what's actually going on there. All right, so we're seeing these kind of typical diagonal lines down here. This means if I put the mouse at the start, you can see at the very start, all of the processes are doing a lot of computation here. And gradually, one by one, they drop off. As we move through, they drop off and go down and wait in this all reduce until the last one's finished, and then they start again in the next iteration. So this is kind of a classic imbalance that you get in with MPI codes. And most of the processes by this point are all waiting for that one guy who hasn't finished yet. Wherever you get kind of a dragged out section like this, that's something that you want to optimize and squeeze up together so you get much more nice regular operations, then the whole thing runs faster. MAP can help us find out exactly what's going on here. Here we have a whole lot of different metrics about what's going on in the program. So there's memory usage. Down here's the time spent in the MPI calls, and here's the amount of time spent doing floating point operations. On this MPI call graph, as we get towards the end, we can see that rank 0 is the one with the most time, 300 milliseconds per call. Rank 3 is not spending any time in MPI at all. That's the guy we're waiting for. And again, on the CPU graph, we see that rank 3 is the only one doing any computation here, and the rest are waiting. So already MAP has told us that your problem is rank 3, everybody's waiting for that guy.
So this is for scientists who don't have MPI as a day job, right? They're not, they don't want to be working on MPI all day. They want to get their code to work, to go fast, right? And this is giving them great insight, isn't it?
Yeah, I think the benefit of a tool like this is that you can get started without a lot of setup, and without knowing the details of how MPI works, you can say, oh, blue is bad, green is good. And I know, all the scientists I know, they're very familiar and happy with working with graphs and tables. They're very smart guys. They just don't need to know the internals of what goes on to get their results out.